Hi everyone, my name is Lennard and today I'm going to talk about Simuliris, a framework for verifying concurrent program optimizations using separation logic. This is joint work with Michael, Simon, Ralf, Hoang-Hai, Robbert, Jeehoon and Dreyer. So modern compilers are applying a lot of smart optimizations to make our programs run fast on today's hardware. For instance, consider the C function on the left. It operates on two integer pointers x and y, and when the value at x is positive, it essentially multiplies the numbers stored at x and y by repeated addition before returning the result. When we ask the Klang C compiler to translate this function, it will do multiple optimizations, and one of them is to hoist the repeated loads from x and y out of the loop, replacing them by single loads into local variables n and m, which can then subsequently be placed in registers. Now, the question of course is how we can be sure that such optimizations are in fact correct. In this case, you might think that it is obvious. As long as x and y do not change during the loop, the optimization can easily be seen to be correct. And that clearly holds true in a sequential setting. In a concurrent setting, however, the picture is less clear. You might imagine that some other concurrent thread also has access to x and y and is changing the value by writing to them, such as in the code on the right. Then, in fact, the optimized program can produce results that the unoptimized program could not. As an example, assume that we execute the optimized program in a state where initially x is 1 and y is 99. First, the thread on the left loads from x and n gets the value 1. Then the scheduler switches over to the other thread and writes the new values of x and y. And after that, the left thread reads y into m, seeing the new value 42, and the remaining code on the left is executed. In this case, the optimized program produces the result 42 by using the old value 1 of x and the new value of y written by the other thread. On the other hand, if we consider the unoptimized program, we can see that it will always read x after y. So if the new value 42 is read for y, then also the new value 2 will be read for x, and there's no interleaving which can produce the result 42. So the optimization seems to introduce new results for the program, which would be wrong. There must be something more going on here. The reason why the optimization is in fact correct is that there is a data race between the two threads in this example, since one thread is reading from x and y while the other is writing without any synchronization. In C and C++, programs with data races have undefined behavior, or short UB. This means that the programmer has to guarantee the absence of data races, and so the compiler can assume that no concurrent thread is writing to x or y. So the optimization is correct, but proving so requires reasoning about concurrent program optimizations relying on UB of data races and involving loops. And while there's a lot of interest in verifying compilers, there's only little work involving data races, and it has several limitations. All existing work either cannot handle loop hoisting, as in our example, or cannot optimize around certain synchronizing operations like atomic reads. As part of our work, dubbed Simuliris, we develop an approach that can handle both. And our key idea for verifying data race optimizations is to employ the concept of ownership from separation logic. Considering the example code again, as our thread is reading from x and y, we know that concurrent writes would be data races, and we can thus assume their absence. Intuitively, this gives us a kind of partial ownership of x and y, which we express through the points to connective of separation logic. Importantly, we do not require this ownership explicitly, but rather obtain it implicitly just from the knowledge that there are no concurrent writes. And we can then retain this ownership throughout the whole loop, and therefore know that the values for x and y do not change, meaning that we can perform the optimization. To use this elegant ownership principle formally, we have developed Simuliris, a language-generic simulation framework based on separation logic. It provides many common proof principles, such as coinduction, and allows the derivation of language-specific principles on top. Our simulation relation satisfies a strong soundness result, namely fair termination preserving contextual refinement. And using Simuliris, we've defined two domain-specific logics on top. First, a logic for exploiting data races as in the example before. And secondly, we have re-implemented and extended the simulation logic from the Stack Burrows paper by Jung et al. Finally, all of this has been fully mechanized in the Coq proof assistant using the Iris framework, and our Coq artifact is freely available and has been deemed reusable. Now, I hope we piqued your interest with this short preview, and we look forward to seeing you for the full talk. Thank you!